new people that came to attend the workshop just starting this week, but I see that about 90%. So how many people did not see the tutorial last week? Okay, good. So what I'll do is I'll try not to bore the previous week attendees too much. What we'll do, so in general, the plan for this week is that Anoop and I will give a short mini course on specifically on interactive compression. This will be a more in-depth course. It will be a more technical tutorial. So, and the plan in general is today to give about a half an hour overview of what most of you already saw. So we'll recap the main notions and properties of information complexity. It will be geared more towards what we actually want to prove. So it will be a more technical overview, but still I'll try to keep it quite simple. We'll only do what we need for the later proofs. And then most of this week, Anoop and I will focus on a more detailed overview of the state-of-the-art one-shot interactive compression scheme. And this will be the focus of, so we'll do a tutorial, we'll take a break at around 10 o'clock, and then we'll see an overview of BBCR's compression scheme that we mentioned last week. Tomorrow we'll see the compression scheme of Braverman, and if we have time tomorrow, then I'll also present some applications of information complexity to areas in distributed economics and to things that go beyond the direct sum application. So this is the plan. And again, so this is kind of this is a course, so feel free to interrupt. We don't really have a tight schedule here, so feel free to interrupt. And the purpose is for you guys to really get out of here with some block of knowledge that is significant about interactive compression. So our setup is once again the two-party interactive communication complexity. Alice and Bob are receiving inputs X and Y according to some joint prior distribution. Their goal is to compute some joint function f of their inputs, or in general, some interactive task. So it doesn't have to be a function, it can be a two-party relation, or any interactive task you can imagine. To do so, they come up with a protocol pi. So this is nothing else but a formalization of a conversation. So each message that a party sends in each round depends only on the input of this player and the history of the protocol. A useful way for stating this property of communication protocols is to say that communication protocols form a Markov chain in the sense that if Alice has input X, okay, so I will say it this way. Let's say it this way. If I is an odd round, so if Alice is the speaker in the next round, then conditioned on the history, this is the history of messages up to round I, the next message is only, okay, so let me say it this way. The message distribution at round I, if I is an odd round, so Alice is the speaker, conditioned on the player's inputs and the history, is the same distribution as if. So this is to say that the next Alice's message in the ith round is conditioned on her own input, and the history of the protocol is independent of Bob's input Y. Okay, and we'll use this fact quite a bit There are many ways, equivalent ways to state this, but this will be the main feature of communication protocols. And we allow the players to share some public random tape which is written in the sky, so they can toss random coins independently of their inputs with no extra charge. And last week we saw that public randomness can be useful for minimizing communication, but in fact private randomness is the more crucial resource when we're trying to minimize information. And the intuition was that private randomness can be used to reveal information very carefully or slowly. So so the point is that you should treat private randomness in this talk as you cannot ignore it. Okay, so we always assume that our protocols have private randomness. The players are randomizing their messages over private coins.
So in the right-hand side, there is also public.
Right. So here we also should have conditioned on public randomness. In fact, for the purpose of this talk, I don't want to confuse you too much, we'll be able to actually fix the public randomness. So the important randomness really will be the private randomness. And the reason is that by the averaging principle, well, let me say something about this later. So the point is that you should only worry about private randomness. Public randomness is essentially, we can essentially ignore it, but for the sake of formality, we just condition on the public randomness as well. And we can define the natural complexity measure, which is the two-party communication complexity of a function f with respect to a prior distribution mu, as the cost of the cheapest protocol, the fewest number of bits that are exchanged in any execution of the protocol pi, which correctly solves the function f with some small error under mu.
Why can't the public randomness just be considered appended to the inputs and part of the distribution?
I mean, I think that would be fine. Yeah, the way I like to think of it is that, I mean, the main feature of public randomness is that it's independent of the inputs, right? So you can feel free to append it to the inputs. The way I like to see it is that, the protocol starts, the first message that Alice sends to Bob is just, she draws some random coins using her private randomness, and she sends it to Bob. This may cost a lot of communication, but for information purposes, this will reveal nothing about the input, and then therefore you can treat the public randomness as the first message of the protocol. And then you don't need to talk about public randomness. There is only private randomness, but that's, I mean, since public randomness will not be an important resource throughout the entire talk, but that's completely fine. Okay, so communication complexity. Any questions? Okay, and so it's a good question. So the convention is that this is a worst case measure. Of course, using Markov, you can always turn this into suppose you have, if the protocol communicates C bits in expectation, then with probability at most, if you're willing to suffer another, to increase your error by a factor of 2, then you can always use Markov and translate this into a worst case. So you can guarantee you can always truncate the protocol, right? So.
You've got randomness, right? Then it's worst case is expected because it's expected. Right?
So it's worst case over the distribution. Okay. I'm saying that, right, when we say the protocol has expected communication, then this expectation is measured over, in this case, the expectation is measured only over the randomness of the inputs, because we assume that we can always fix the randomness when we're interested in communication. Okay, I agree this is confusing. So let me just say one principle you should keep in mind that maybe that will do though. For communication purposes, we can always fix any kind of randomness just by the averaging principle. When we have some prior distribution, there's always, by the averaging principle, there's a fixed random string that will achieve the same performance under the input distribution. When we start talking about information, which will happen in a few minutes, then we cannot afford to fix private randomness because it will be crucial to leak little information, okay? And I agree this is confusing, but so yeah, feel free to interrupt. But that will be the guiding principle. Okay, so any questions?
And you mean that the joint distribution is known to both players, right? I mean, mu.
Yeah, sure. Mu is public knowledge. The protocol tree is public knowledge. The only thing that is not known is the actual realization of the input. All right? And as we saw last week, there are a lot of motivations for studying communication complexity, ranging from mechanism design to chip design. And I will not, this will not be the focus of this talk, but for those of you who are not familiar with it, just take my word for it that there are many applications for which the best lower bound on the resources in many models beyond communication complexities, such as streaming models and privacy, number of wires in a circuit. All these complexity measures, we have methods for proving lower bounds on these models using communication complexity. So there's a lot of motivation for studying this complexity measure. And really the take-home message is that if we develop new tools in communication complexity, we potentially make big progress towards many other fields, understanding many other fields of computer science. Okay, and as we saw last week, we can define we can look at the length of the communication as the communication cost of a protocol. But at least when there's a prior distribution on the inputs, it makes sense to also look at the information that a protocol leaks to the parties about each other's inputs. And we'll try to formalize this, and most of you have seen it last week. So in this case, instead of looking at the number of bits communicated, we're asking ourselves, how much does Alice with input X learn about Bob's input Y by observing the protocol transcript Y and vice versa? Okay? And to formalize this, we will use notions from information theory. So the most basic measure in information is the Shannon entropy of a random variable. This is just the expected number of bits required to describe a random element of the distribution. So for example, the entropy of a random unbiased coin is 1. Okay, this is irrelevant to the talk. So the conditional entropy is just the expected remaining entropy in X when we condition on an average realization of Y. And perhaps the most central measure perhaps the most central measure we'll use is the mutual information between two random variables, which is just the mutual information between X and Y, which can be interpreted as follows. So it's the average entropy remaining in X, right? So yeah, so we draw a random variable Y, we condition on it, and the average entropy that remains in X, this area here, is the mutual information. So it's the average residual entropy that remains in X when we condition on a random variable Y. Okay? And finally, we'll use the notion of a conditional mutual information, which is the average information that X reveals on Y when we condition on a random variable Z. Okay, and this is essentially all we will need to formalize everything we need. Okay, and we'll use the chain rule for mutual information, which just says that
Nothing changes this formula. As it should be the same, I think. Because if x, y, and z are independent, it's just x of x minus h of y.
Y
which
and
is
x are
zero.
transposed in the
Yeah.
last.
So where is
There
this?
is an error that y and x should be exchanged in the last entry.
Because
Here?
It's just a typo, yeah.
Oh, so
It's just a typo.
so this is okay, and this is. Oh, sorry. Everything should be replaced with I, of course. Sorry.
All right.
Right? Everything. So the information that X reveals on Y condition on Z can be decomposed as the information X gives.
No. It's essentially
It's
Courant, just
yeah. Anyway, let me just write it here. The information that X gives on Y. Okay, so yeah, well, I guess.
No, that's not it. X given z. X given
Sorry.
z.
Yeah, just delete the y first.
The yeah, sorry. Too early in the morning. Sorry. All right, so yeah, so that's so these are all the tools we will need, and we can now define the information cost of a protocol pi. So remember, in this terminology, we can always view a protocol pi, the transcript, as just a random variable of the joint input distribution x and y, right? So when we treat pi as a random variable, the transcript is a random variable. We can define formally this, the information cost of a protocol pi with respect to mu as the amount of information that pi reveals on Alice with input x about Bob's input y, and vice versa for Bob. And once again, we assume that we just suppress, throughout the talk, we suppress the public randomness. So we assume that implicitly we're conditioning on the public randomness R. And so is this, any questions about this quantity? Is that, so this will kind of accompany us throughout the entire week, so. All right, so for example, the information cost of the trivial protocol in which the players simply exchange their inputs is just the sum of the marginal conditional entropies, right? And just a remark, notice that the communication cost of this protocol can be arbitrarily larger. The communication cost is just 2n, right? Assuming the input size of the players are n bits. And this quantity, while this quantity might be arbitrarily smaller, right? And so this will kind of recur throughout the talk, but this is just an observation. And we can also define a different measure of information, which is called the external information cost, which intuitively captures what an external observer learns from the conversation for the protocol transcript pi about the player's inputs y. And it's not too hard to prove that the external information cost is always an upper bound on the internal information cost. And the reason is that, the intuitive reason for that is that an external observer is always more ignorant to begin with. So information cost is always measured with respect to the prior distribution. And an external observer is always, the entropy of the distribution mu for an external observer is always larger than of either Alice and Bob because they have some side information about it. So this is, I will not prove this formally, but this is the case. And we will mostly focus in this talk on the internal information cost. And we will see this, I guess that by tomorrow it will be clear why this is the measure that is more interesting, at least for the applications we will discuss this week. And so, yeah, so from now on, this will be the main complexity measure we'll work with. And we can now just define the information complexity of a function to be the minimum amount of information the players need to disclose each other in order to correctly solve the function f with some small prescribed error under the input distribution mu. Okay, so previously we had, remember, for the communication cost, we were minimizing the amount of communication. Here we're minimizing the amount of information. Right, so a few quick remarks, which I hope most of you will not get bored by. So first of all, this is unlike the standard setup in information theory, this is a one-shot measure. So there are no multiple blocks. This is not an asymptotic setting. And as we said here, regarding your question, this is an average case measure, simply because information is defined as an average case measure. Again, this will not be such a big deal, but this is one difference between information and communication. As we said, private randomness for the purposes of this quantity are crucial, and we will see this in the future of the talk. And so we should always keep in mind, or we should always assume that the messages of players are always randomized using private randomness. The last remark is that this infimum, unlike communication, cannot be replaced with a minimum, right? So in the setup of when we're trying to minimize communication, we can always, our loss is always bounded, right? We can, the trivial upper bound is just exchanging inputs. This gives a trivial upper bound of 2n, or let's say n plus 1 bits on any communication function, right? Alice can always just send her entire input. This is not the case with information. So in fact, if I have time tomorrow, we will see an example where of a function where the information optimal protocol reveals less than 2 bits, but if you want to be information-wise optimal, you need infinite communication. There is no finite communication protocol that achieves the minimum information. And once again, the intuition for that is that, unlike communication, if you want to be information-wise optimal, then you need to reveal information in a very slow fashion, in a very careful manner. Okay? And we'll see some examples, hopefully, throughout this course. Okay, so these are the only remarks. And now, so the natural question which will be interested is, what is the relationship between these two complexity measures, the information cost and the communication cost of a function f? And we'll try to answer this question over the next couple of days. Just to give you a spoiler, the bottom line is that the question is still quite open. So despite the significant progress that was made over the past few years on this question, I will give a disclaimer that one of the exciting facts is that we actually still don't know. So over the next 2 days, I'll try to convince you why this question is interesting and try to show you what has been shown regarding this relationship. Okay, so what I claim, nevertheless, is that one direction of this relation is very easy, actually. So it's easy to see that the communication cost is always an upper bound on the information cost of any function. In fact, this holds pointwise for any protocol. And the reason is very simple, is that 1 bit of communication can never reveal more than 1 bit of information. Right? So one direction is clear. How about the other direction? So the first to consider this relationship was Shannon in his classical 48 paper, where he showed that at least in the transmission setup, where only one party speaks, when there's only one round, then the amortized communication cost of transmitting a random message m to a party with, let's say, no side information scales precisely as the information that this message contained, the entropy of the message, h of m, and this is known as the Shannon's noiseless coding theorem. And in fact, well, Anoop corrected me about this. maybe the information theory people know. So was this okay, so what I claim is that in fact a much stronger statement holds for the transmission setup, namely that even in the one-shot, so not only asymptotically does this inequality hold, but if we don't care about this extra 1 bit, which we will in the future of this talk, then in fact a much stronger statement holds. We can, the amortized communication of M equals up to 1 bit to the entropy of this, of the message. And we can do this even when we're given a single realization of M. And the code that achieves the optimal rate in this setup is the well-known Huffman code. Okay. So, but the point of this slide is that in this talk, we would like to really distinguish between so-called amortized and one-shot compression results. And obviously, one-shot results are much stronger. In this case, this result obviously implies Shannon's result. And we will focus mainly on the relationship between the two and on the implications of this relation. So since these two classical theorems, information theory was developed in many other ways, and compression was generalized to many other setups. For example, a well-known example is the Slepian-Wolf theorem, which states, morally speaking, that the same tight bounds continue to hold even if Bob has some side information Y about Alice's message or Alice's input M. And so all these examples show that at least asymptotically, information keeps giving the tight correct answers for communication problems, right? But the question is, and the natural question is, what happens for the interactive setup, right? So everything we saw so far was just for, in the last slide, was just for a one-round or one-way transmission setup. The question is, what happens when the conversation is interactive, when there are lots of rounds of interaction? And this is precisely the question of interactive compression, right? So suppose Alice and Bob engage in a protocol that reveals 1 million bits so the conversation communicates 1 million bits of communication. But suppose that the information cost is very low. It conveys only, let's say, 8 bits of information. The natural question at this point is whether the parties can simulate this conversation more efficiently, right? It makes sense that most of the time the parties are not learning anything, so they might be able to simulate this conversation more efficiently, and this is exactly the interactive compression question, which we will formalize very soon. So can we compress conversation in the interactive setup? And the answer, perhaps quite surprisingly, is that yes. Well, at least in the asymptotic case, Braverman and Rao recently showed that basically they proved an interactive analog of Shannon's coding theorem, showing that the amortized communication complexity of computing many independent copies of any interactive function f scales precisely as the single copy information cost of this function. Any questions about this theorem? So just, is the statement clear?
No. You really mean that the joint distribution for the k-wise extension is IID?
Right. So what is the, so the quantity up here is the number of communication bits required to solve k independent inputs, where x1, y1, x2, y2. So fk is defined as the following k tuple functions. Okay, so it's a k-bit vector, and the goal is to output the answers to each one of the copies. And the theorem states that if we want to compute the amortized communication cost of performing this k-fold task with a per copy error, with an error of epsilon, let's say an error third on each copy, per copy, then the communication cost of this k-fold task scales precisely as the information cost.
What I meant was that mu is now extended to sequences, and it's extended
Sure.
by independence.
Yes. So,
We really should have written mu to the k.
right. Oh, sorry. Sorry. This, yeah. So I should have put here mu to the k. Sorry.
And how does this relate with external information complexity? So is it also equal, or?
So that's a good question. Let me comment about this in a second. So up until this slide, this information was a standalone measure, and we're free to define whatever we wish. But this slide really shows that whether you like this measure or not, you cannot ignore this, because this has an operational justification, right? The single copy information cost is a characterization of the amortized computation, and in fact, not only does it characterize it, it's a very robust characterization in the sense that this was a follow-up result that shows that basically this theorem is tight. In what sense? Well, not only do you need k times the information cost bits of communication to compute k independent copies, but any protocol attempting to solve k independent copies of any function f using significantly less than this number, than k times the information cost, it will fail with it will succeed with exponentially small probability. Okay? So this shows you that information cost is a very sharp characterization of amortized computation. You cannot, yeah.
What is the quantification of our mu there? Is that for some mu?
No, for every, so this theorem holds pointwise. So the statement is the following: fix your favorite interactive function and your favorite distribution mu. Then the communication cost of solving simultaneously all the k independent inputs under this of f under this distribution mu. If you ever try to solve this using significantly less than k times the single copy information cost with error a third, then you will succeed only with exponentially small probability. And of course, this is tight, right? You can always, this matches the communication cost and success of the naive protocol that just applies the per copy optimal protocol sequentially and independently to each copy. Okay, so this is just a side comment. We'll not dive into this type of stronger results, but one way to view this is a sort of a parallel repetition theorem for those of you who are familiar with, or as a so-called Arimoto converse theorem for information cost. But
So just to understand the definition, if on the right-hand side you would put f k divided by f then it wouldn't matter anything on the right-hand. The definition.
sorry, here?
Yeah.
If we divide it by,
Put f k and then divide by k. The same,
right.
then it wouldn't matter.
We will see, this is the next slide, so we will see this in a second. Okay, but so this was just a side comment to convince you that this is this measure has an operational meaning. To answer your question, we do not have an analogous operational interpretation of the external information cost measure, and I think it will be very interesting. We had some conjectures, but it's not clear. This is just a...
Just one comment. I think when you said an Arimoto converse, you just mean strong converse. Arimoto converse is a strong converse for a particular problem.
Well, not quite. I mean, it's even stronger, because strong converse just means that the probability of error, if you are over the threshold,
Tends to 1, right?
tends to 1 rather than
Seems like
not converging to 0. That's strong converse, but this is just terminology.
Right.
And if you have exponential decay, then
But it seems like all strong converses we know exhibit this exponential decay.
the II decays, yes.
Yeah.
Okay, thanks for
My
that.
point was that the error model converse refers specifically to the chain coding converse, right? Yeah. It's a strong converse for that.
Yeah, this is why I put it in like quotation marks, but yeah, sure. Okay, so what I want to focus on in the next, what time is it? Yeah, so in the next 10 minutes before we move into the actual compression scheme descriptions, I just want to prove to you at least one direction of this theorem because it will exhibit the most, I guess, remarkable or the most important feature of, or property of the information cost measure, which is the fact that information complexity is a purely additive, is a strictly additive complexity measure. Okay, so let me try to prove to you the greater than direction. And what I claim is that it suffices for this direction, suffices to prove that, we'll in fact prove inequality here, that the information cost of computing k independent copies, again, this should be mu to the k. So the information cost of computing k independent copies of any interactive task, of any function, is with per copy error of epsilon, equals precisely to k times the information cost of a single copy. So it's a strictly additive measure, and this will be very, so another way of saying this is that any protocol solving k-independent copies of a function, the average information it reveals on a random index is what it reveals, the overall information divided by k, by the number of copies. Make sense? Does this parse this? Okay. And of course, again, because information is always a lower bound on communication, this will prove that the communication cost of solving k-independent copies will be at least as large as this copy. And this will finish the first direction of the theorem. So what is the idea of the theorem? And really, so every talk has like 0 or 1 important slides. This is the one. So try to bear with me for another few minutes. So what is the idea of this theorem? We'll see this recurring throughout the talk. So we're given, we'll try to prove this in a contrapositive fashion. So suppose we're given a protocol pi for k copies of the function f, and let's denote the information cost of this k-fold protocol by I. Our goal will be to produce a protocol for a single copy of the function f, which uses roughly I over k information. That will prove the theorem. So any question about the logic of the argument? Right? So to carry out this, this approach, we would like, Alice and Bob would like to take a single copy of the distribution mu, their own inputs x and y, and they would like to embed it to the k-fold protocol pi and run it, and somehow hope that because pi should reveal on average I over k bits of information on a random copy, they can hope to just run the protocol and hope for the best. So let's try to formalize this intuition. So remember, Alice and Bob would like to generate a protocol for a single copy. They can try to embed their inputs into a random coordinate of the k-fold protocol. But now if they want to run the k-fold protocol pi, they cannot just run it, right? It's not even well defined at this point because pi expects to receive k-fold inputs, right? So they cannot simply run this protocol. They have to somehow complete the missing entries for this protocol, right? And as we saw last week, the natural idea for how to complete these inputs is to just sample them using public randomness, right? So they can just try to sample all the rest of the inputs publicly. This turns out to be a bad idea because it will leak too much information. And the way to see it is, suppose the players sample all the rest of the inputs publicly. So in particular, Bob will see all of these remaining inputs. And suppose these are just bits. If the first message of the protocol pi is to just send the XOR of all of those bits, then Bob will actually learn a full bit of information on X because he will know the XOR and he will know all of those inputs. This will leak a full bit of information about X while we are shooting for revealing only 1/k bits of information. So the point is that sampling, completing the rest of the inputs using public randomness is a bad idea. The information will go through the roof. That's too expensive. Okay, fine, so let's try the other extreme. Let's try to sample everything using private randomness. What's the problem with that approach? It's a joint distributed. It simply cannot be done, right? X and Y are correlated through mu in each copy. There's no way the players can privately sample it, right? Well, then we seem to be, so public doesn't work, private doesn't work, so what else do we have? And the novel answer for this is that we actually combine the both. So what the players will do is they will sample publicly only Alice's inputs up to the index I, and only Bob's inputs up to index n. Intuitively, this leaves enough entropy in each coordinate so that the information will remain low. But this completely enables the rest of the sampling task because conditioned on Alice's input X, Bob can now privately complete his inputs to the remaining coordinates and vice versa for this part. Does that make sense? This will be...
It's to suggest that if you actually wanted to do this in a sort of a more of a cryptographic example or something, you'd be in trouble.
So what...
I mean, something where it's harder to sample the arguments given.
Oh, I see.
Not everything is the polynomial time sampleability is not going to survive easily.
I see. You mean for
Maybe the
completing the...
can be sampled polynomial time, but not.
I see. Not the conditional.
Not one of them given the other. Maybe one of them.
I see.
Maybe X given Y, yes, but not Y given X.
I see. I never thought about. Yeah, it's interesting.
Also, it's strange why the order is playing so important role, actually. Why you decide less or greater than everything is symmetric.
Oh, it will only simplify. You can equivalently, for each coordinate, you can equivalently just draw a random coin with probability half. But this, you'll see that this will be easy to apply the chain rule in a second. So.
I was just going to say that, so this idea is not occurring in this paper for the first time. There's a long history of these splitting variables in computer science, and then Chandler was telling me that also showed up in the information theory side for a long time. So it's a common technique that shows up in many cases where you must split the dependence. And sort of
Yeah.
the case where you're independent.
Right.
variables.
Right. So I guess the moral of this technique is really that we want to break the dependence between the inputs in a way that in a way that sufficiently a sufficient amount of entropy remains in the inputs, right? So the trivial way would be to just publicly sample it. Then we're in trouble, as we saw. But okay, so is everyone convinced that at least after this outline is performed, the entire input distribution to the protocol is perfectly well defined, and each copy is distributed correctly according to the independent distribution mu. Okay, so now the players can just run the protocol pi. From this point it's clear, right? The players so this just describes what we saw, and the players just now, once they have sampled everything, they just run the protocol pi, and they output the ith bit of the output. Okay, so by the premise, remember, pi was a protocol with per copy error epsilon, right? So it's a correct protocol, right? In particular, it outputs the correct answer to the ith copy with probability 1 minus epsilon. So all that remains is to analyze its information. Okay, so let's do that in the remaining 5 minutes, and then we'll take a short break and we'll come back. So what is the information cost of this single copy protocol theta? Well, by definition, this is the information cost. Let's look at the first term, right? An analogous argument will apply to the second one. So by the definition of conditional mutual information, the information cost, the information that theta reveals on X is just, we just unfold or unravel the public randomness. Remember, the protocol theta was embedding X and Y to the ith copy with uniform equal probability. So with probability 1 over k, we're measuring the information that pi reveals on the ith input. Does that make sense? Okay, and remember, we always condition on the public randomness. The public randomness is always the previous Alice inputs up to a coordinate I, and the remaining n minus I coordinates of Bob. What I claim, and this is the only non-trivial inequality I'll use, is that we can always replace this, the information with the conditioning. Instead of conditioning on the last n minus I coordinates, we can afford to condition on the entire input of Bob, the entire n coordinates. And this can only increase the information. Okay, why is this true? It's a one-line inequality, but the intuition is that we added conditioning here on all the coordinates y1 through yi, right? And the point is that these coordinates condition on what Bob knows and the public, on what Alice knows and the public randomness. These inputs are independent of Alice's knowledge, and conditioning on additional independent information can only increase the information. If you want, I can show this in the break. It's a very easy inequality. Okay, so if you believe this step, what did we achieve by this? Now this random variable is independent of the invariant I. So does this remind you anything? This term just screams the chain rule, right? So this is exactly the chain rule for mutual information. This is exactly equal to, we can just collect all the x's, and this is just, by the chain rule, equal to the information that pi reveals on x condition on y divided by k. Okay, so this is the entire trick. This is the, any questions?
But you left out the division by k, right?
Sorry?
1 over k is, oh, sorry,
Yeah.
It's there.
Yeah. So I want to say the entire point here is that we use the chain rule, but we still got to keep the 1 over k. This is exactly what makes the information. So this calculation just formalizes the intuition that the information a k-fold protocol reveals under this sampling method on a random input I is exactly the total information divided by k, by the number of copies. And of course, an analogous argument, this sampling method was completely symmetric with respect to Alice and Bob. So just repeating it from the Bob's perspective gives us the same for Bob. And this concludes our theorem. Okay? So the conclusion from this part of the talk is that information is additive, completely additive measure. And in particular, I'd like you to remember for the next part of the talk that, so this will be a recurring argument. If we take a k-fold protocol with information I, we embed into it, using this sampling method, we generate from it we can always generate from this k-fold protocol a single copy protocol whose communication is very bad, it's the communication of, sorry, it's the communication of the protocol pi, but the information is very good. It's what it was divided by k. Okay, so with this principle in mind, let's take like a 5-minute break, and we'll come back to the compression.